Woohoo! It's a great day for some pre-calculus. I'm Miss Lake Battles, and I'm here today to work through some example problems involving polar coordinates. For the examples that I've chosen first, it says to indicate if the point with the given polar coordinates is represented by A, B, C, or D on the graph. So number 2 says 3 and then 315 degrees. So the first thing we're going to do is look at the terminal side of that 315 degree angle. We start on the positive x and we go all the way to the fourth quadrant halfway. When we go all the way to the fourth quadrant halfway, and then we're going 3 units from the origin, and we can see that brings us to point D. Next, we're going to look at negative 3 pi over 4. So first we want to look at where the pi over 4 would be. The terminal side of pi over 4 would be halfway here in the first quadrant. However, negative 3 means that we're going to go out the ray that's opposite that terminal side. So when we do that, we go out to C. So the answer to number 4 is C. Then for number 6, negative 3, 0. That means my angle is 0. So the terminal side is the positive x-axis. But negative 3 means I'm going the opposite ray from the terminal side, which would be this direction, would be to the left 3. So that's where we find B. Now, one more thing that I think we can do that will help us make sure we understand the difference when R is positive and R is negative is to look at other ways to name these points. For example, if we start with point D here, what would be another way to name D? We named it with a positive 3. Could we rename this with a negative 3? Okay, so what would be the angle measure if originally it is 315 degrees? If it's negative 3, what would the degree measure be? Well, opposite from that, over here, what would be halfway in the second quadrant? And that would be 90 plus 45, which is 135. So notice that these are equivalent. I'm going to get the very same point if I go 3, then 315 degrees, as I do if I go 135 degrees, which is halfway in the second quadrant, but go the opposite ray of that terminal side, which would put us back here in the fourth quadrant. So that's the same as D. Let's write it over here. This is another way to write it. Negative 3, 135 degrees. Now, next, let's look at C. C is over here in the third quadrant. It is negative 3 pi over 4. So what if we want to write that in terms of positive 3? Okay, that would be down the terminal side of the angle. So what is the angle measure starting at the positive x and going around to C? That would be pi plus pi over 4, which would be 5 pi over 4. So that would be the same as 3, 5 pi over 4. And then for the last example, for B, B is written in terms of a negative 3, but what if we wanted to write it in terms of a positive 3? Instead of negative 3, 0, if we're going positive, that would be from the positive x all the way around to B would be pi. So 3 pi is the same as negative 3, 0. So these are some examples to help you understand when R is negative. Next, let's look at this problem. Select the representations that do not change the location of the given point. So from the previous examples, we know that there is more than one way that we could write a point with polar coordinates. So I've plotted this point for us, -2, 7 pi over 6. So when I go from the initial positive x-axis, my terminal side is right here. I've illustrated that in blue. But since the 2 is negative, we're going on the opposite of that ray, which brings me to this red point that I've plotted. So let's look at A. Could -2, -5 pi over 6 be the same point? Well, if I start at the positive x and go -5 pi over 6, that's exactly the same place as 7 pi over 6. So when I go -2 on that, I do get to exactly the same point. So A is the same. Okay, what about B? -2, -pi over 6. You know what? That's going to be in the second quadrant, because when I go -pi over 6, it's in the fourth, and then -2 is opposite from that. So that's a quadrant 2, so it's a no for me. On the C, 2, -pi over 6, well, -pi over 6 again, that's going to be in the fourth quadrant. If we go +2, that stays in the fourth quadrant. So, our point is in the first quadrant. So this is also a no for me. Now the final one is pi over 6, which is here in the first quadrant, and we're going out 2 from that. So yes, that is a great way to write those polar coordinates. Now we're going to look at an example where we change from polar coordinates to rectangular coordinates. In the previous video, we talked about how to do that. So remember, this is in the form r theta. So we want to change it into rectangular coordinates, which would be in the form x, y. So what we learned is that x is the same as r cosine theta. So in this problem, x would be equal to r is 6 and theta is 180. So cosine of 180 degrees. So finding those values, I know that cosine of 180 is -1. So x is -6. Then to find y, I know that y is r sine theta. So y equals r, which is 6, times sine of 180. So y equals 6 times sine of 180 degrees, we know is 0. So remember, sine is the y-coordinate at 180 degrees. So that's at the point -1, 0. So that's why it's 0. So y is 0. So we have now converted from polar coordinates into rectangular coordinates, which of course would be -6, 0. Okay, I have another example prepared for you. It's number 35, 2 pi over 3. So let's do the same thing. X equals r cosine theta. So for this problem, it would be r is 2 times cosine of pi over 3. So x equals 2 times cosine of pi over 3 is 1/2. And of course, 2 times 1/2 is 1. So the x coordinate is 1. Y is r sine theta. So y equals r is 2 sine of pi over 3. Might help you to remember that pi over 3 is 60 degrees. So that's 2 times, and sine of pi over 3, 60 degrees, is square root of 3 over 2. Of course, the 2's are going to divide out, and we just get y equals square root of 3. So now I've changed these polar coordinates, 2 pi over 3, into rectangular coordinates, which would be 1 square root of 3. In this example, we're going to change from rectangular coordinates to polar coordinates, and we need to express theta in terms of radians for this problem. So, recall from our previous notes that we used the Pythagorean theorem to get r squared is x squared plus y squared. I told you then that that would be a way we would change from rectangular to polar coordinates. So, substituting into my problem, r squared equals 2 squared plus negative 2 squared. So r squared is 4 plus 4, which of course is 8. So r is the square root of 8, which I'm going to simplify. Remember, it has a perfect square factor of 4. Square root of 4 times square root of 2. So that gives me 2 square roots of 2. Now, next we want to find theta. So to find theta, recall that tangent of theta is equal to y over x. So in this problem, tangent of theta is equal to y is negative 2 and x is positive 2. So that gives me negative 1. So remember, what we're really finding is the inverse tangent of negative 1. That will give me theta. So of course we know that the reference angle for this would be pi over 4, because tangent of pi over 4 is positive 1. But we know which quadrant this is in. A positive x and a negative y is going to put us in the fourth quadrant. So let's write that over here, fourth quadrant. So if the reference angle is pi over 4, and remember, we're supposed to put this in the interval 0 to pi. Let me write that also. We want it in the interval 0 to pi. So when I put that in the fourth quadrant, my pi over 4 in the fourth quadrant, it's going to be negative pi over 4 or 7 pi over 4. So let's write it that way, 7 pi over 4. Again, I know that it needs to be in the fourth quadrant. So r theta would be 2 on the square root of 2, 7 pi over 4. I've chosen another example, the very same kind of problem. Work this along with me here. Maybe you'll be able to finish it before me. Remember that r squared equals x squared plus y squared. So in this case, r squared equals negative 2 on the square root of 3 squared plus 2 squared. So r squared equals, of course when I square this negative, it's going to become positive. 2 squared is 4. The square root of 3 squared is just 3. And then of course 2 squared is 4. So 12 plus 4, 16. R squared is 16. So r is 4. Now, I want you to note here that, again, in rectangular coordinates, it's negative, positive. So this is going to help us with the angle part. We're going to be in the second quadrant if it's negative, positive. So let's think about that when we find theta. Tangent of theta is y over x. So tangent of theta is 2 over negative 2 on the square root of 3. Okay, it's going to divide out. It's going to give me negative 1 over the square root of 3, but we know if we rationalize that, it would be negative square root of 3 over 3. So what we're really finding here is the inverse tangent of negative square root of 3 over 3. And remember, we need this in terms of radians, so we're going to have to remember those trig values. So my reference angle would be pi over 6. Okay, let me jot that down. Reference angle is pi over 6, but I know that this is in the negative positive second quadrant. Okay, so I'm going to put pi over 6 in the second quadrant. So that would be pi minus pi over 6, which would be 5 pi over 6. So my polar coordinates here would be 4, 5 pi over 6. Okay, hang with me, we're almost there. I have these two examples to convert each rectangular equation into a polar equation that expresses r in terms of theta. So, beginning with number 50, what I want to remind you is that x is r cosine theta. So I'm going to make that substitution. X is r cosine theta. Now, y, I'm going to substitute in there as well. That's r sine theta. And that, of course, is equal to 8. So I just made a substitution. X is r cosine theta, y is r sine theta. So now I'm going to factor out an r that's in both of these. Okay, when I factor out an r, I'll be left with cosine theta plus 5 sine theta. That's equal to 8. Now I want to express r in terms of theta. That's why I factored the r out. I want r by itself. So what we're going to have to do is divide both sides by cosine theta plus 5 sine theta. And when we do that, of course, all this will divide out, and dun-da-da, we'll be left with r equals 8 divided by cosine theta plus 5 sine theta. Okay? Oh, that's a little messy. I'm going to fix it. There. Now we did exactly what they asked us to do. We converted the rectangular equation to a polar equation that expresses r in terms of theta. So let's look over at number 54 and let's do the same thing here. Let's make that substitution that we talked about. In place of x, we're going to put r cosine theta. And we're going to square that. And then in place of y, we're going to substitute in r sine theta. And we're going to square that, and that's equal to 16. Now, I've got to square these. That's going to give me r squared cosine squared. Remember, this is the shortcut way we write cosine of theta squared, the quantity squared, is just we write it cosine squared theta plus r squared sine squared theta equals 16. Now, I'm going to factor out my r squared, and I'm left with Oh, something that looks very nice. Cosine squared theta plus sine squared theta. Ding, ding, ding. I hope you're thinking, that looks familiar. Yes, this is an identity. It's the Pythagorean identity. That is equivalent to 1. So that simplifies it a lot. R squared is 16, so R is 4. Now, this makes lots of sense. Look, my equation is an equation of a circle. Center's at the origin, the radius is 4. So this is my final equation here. Okay, final example. If a horse in the inner circle of this merry-go-round is 5/6 of the way around, we want to find its polar coordinates. Okay, this would be so easy. We want to be 5/6 of the way around, so that's 5/6 of 2 pi, which would be all the way around. So of course that would be 10 pi over 6, which would reduce to 5 pi over 3. So that is theta. Now I want to find r, and that's actually shown in the illustration. We want to know the radius. It's on, the horse is on the inner circle. So the inner circle would be, it's shown right here, 6 feet. So r theta would be 6, 5 pi over 3. And that's it. I hope this has been helpful for you. I look forward to seeing you later. Have a great day.